find be the third token, right? So when we split by spaces, our responses for the amount of tokens or the sequence of tokens would be different, right? So I hope this part is clear. Tokens are small portions of our input text that carry some meaning by themselves and are processed by our model, right? So we break down a large chunk of text into small individual portions, right? Now we have dealt with words here as a tokens. Now instead of, let's say, a single sentence, we had tens of thousands of documents. In that case, if we use a single word as a token, it can be a bit hectic. So we can use entire sentences as a token as well, right? So instead of breaking the large multiple document text into individual words, we will break down into a sequence of sentences. Similarly, we can also do this thing based on n-grams. N-grams, I believe the back of word model was introduced. So the idea is that a sequence of, let's say, words you can think of. Gram here can be a unit of a small unit of a text, right? So you can think of gram as a another abbreviation for token. So n number of tokens you can think of as n number of words, n number of characters, or however you want to do it, right? Obviously we can also break down our text into as a sequence of characters instead of a sequence of words. In that case, our first token would be h, second token would be I, third token would be space, and so on, right? So this is the general idea of tokenization. Similarly, let's say we do tokenization here based on sentences. So this particular same sentence, when tokenized based on sentences, the first sentence, which is um, where this one. So this will be the first sentence. Hi, Mr. Smith. I am going to buy vegetables, tomatoes and cucumber from the store. And then should I pick up some black-eyed peas as well? So you can think of it as these three sections if you are taking any punctuation mark as a end of sentence, right? However, when you are doing this, you can also consider, okay, maybe the sentences ended here where there was a closing bracket, right? So this kind of sentence tokenization can be very tricky, and we need to make a very specific and predefined rules on how to structure them. Similarly, let's say we use a sentence tokenizer already present in the NLTK tokenizer, and then we can just pass it and it will give us the same three sentences, as I said, right? Breaking the sentences based on exclamation mark, full stop, and question mark. N-grams, you can think of similarly, as I said, groupings of n number of tokens. Here we have set the n as 2, right? So it will be a grouping of 2 tokens or 2 words, let's say, right? So hi Mr. is 1 token, Mr. Smith is 1 token, Smith exclamation mark is 1 token, and so on, right? So this is the general idea of n-gram, very similar to in concept to the bag of word model, where we are treating consecutive words as a singular input, right? If we change this particular n value from 2 to 3 in the n-gram, we will get hi Mr. Smith as 1 token and Mr. Smith exclamation mark as the second token, and so on. Now, another important factor in parsing our text for natural language processing is regular expression, right? So what regular expressions will do, it will allow us to basically format our input into specific kind of structure, right? So for example, phone number you can say is a 10-digit number starting from maybe 6 or higher number, right? So similarly, certain kind of values you can define based on certain kind of structure, right? So for example, name would be first letter capital and then all the letters small, space, then another capital letter followed by a bunch of small characters, then space, and then there may or may not be a repetition of this process, right? So it could be a sequence of one or more words, right, with the first word capitalized. Hmm. Okay, what we have done here we have defined a regular expression, let's say, to tokenize our input, right? And how do we apply this particular regular expression, where our explanation is it should be something after a space, right? Something after a space, anything could be possible, but after a space, a new token should be there, right? So we can define these kind of uh, regular expressions and then apply the regular expression tokenizer to parse our text as well, right? And this slash space plus acts exactly as a white space tokenizer, right? So basically we are splitting our text based on spaces. That's pretty much it. So the main idea of tokenization is that our entire text is too long to be processed at once. So we'll break down our text into chunks of small relevant information or data, right? That's the general idea. And then that is how we apply tokenization, right? I hope there are no more questions regarding tokenization. If you have any questions, you can just add those questions in the chat. If you're not feel like speaking. Okay. Right, so we are done with tokenization, and the second idea is remove characters. Right, so what kind of characters we want to remove? The characters that do not hold any specific value. Now, rudimentally, you can say that all characters will hold some values, even full stop will have some meaning to it. But the general idea is that for our majority of tasks, let's say we want to do classification, or maybe let's say we have a review of a movie and we want to classify this particular review as positive or negative, right? So if we want to do these kinds of tasks, we do not really want we are not really interested in punctuations or capital letters, right? We are interested in specific words, right? Words that may carry a positive or a negative meaning to them, right? So for the task associated with natural language processing, uh, in this machine learning models that we'll be using, we are not really interested in information like punctuations, capital letters, or numbers, right? So what we will do, we'll remove these particular kind of specific information, right? And how do we remove it? We can just remove it by again creating a regular expression that specify all of these criteria, right? So punctuations, we can remove it by just writing the word re.escape string punctuation, because it is a common operation. It is already predefined in our regular expression library, right? And all the punctuations are already defined in the string library. So we can just directly use regular expression dot escape and then escape all the punctuations, and then we can print the text. And here we can see that all of these punctuations, right, these first and last commas, right, determine that the particular input is string. So these would not be removed obviously, but all of the useless information. So for example, I am had a like a dash in between, right? All of those information, all of this Smith, after Smith you had an exclamation mark. All of this information is removed, right? So this way we will be removing all of this useless information, right? How do we make all text lowercase? We could just use an inbuilt Python function which is called lower, right? So whatever string that we have, which is stored in clear text, so clean text has a punctuation removed version of the original input string. Mr. Smith, I am going to buy vegetables, right? Now for this punctuation removed version of clean text, we will just write clean text.lower and we will remove all the capitalized characters, right? And similarly we can remove all the digits as well. So for example, clean text re.sub slash w star w, all the w star, right? So the idea is that any combination of words in between any digit, so we'll clean that, right? So slash d here denotes the digits. So let's say in our input, did we have any digits? We had 21 lbs, right? 21 pounds. So when we apply this method, we have removed the entire part of 21 lbs here, right? This is one of the way of removing, let's say numbers. Maybe you want to keep the lbs part, only want to remove the 21. You can also write for that. Okay. Now, these are the tips and tricks of Lambda. This generally forms under the Python training. So I'm going to skip this particular part. But the general idea is that Lambda function is a method of writing simple functions into one line instead of two or three. Right. So this just allows you to type the values quickly. It is not really that mandatory. You can just write a simple function and it will do the same task anyways. Right. Now, what are the stop words? Stop words are commonly used words that are very common in text but hold little to no meaning, right? Little to no semantic value. Right. So what we want to do, we want to remove all of these stop words as well. What are the stop words? Here is a list of uh, stop words that are present in English language that are stored in the NLTK corpus, but isn't under weren't, so it would be were not, is not, so they were abbreviated, so it would be ISN uh, comma T, right? So it would be so single inverted comma and T, right? So instead of writing the whole thing, ISN is what remained, right? Those, when, why, few, all of these are stop words that carry little to no meaning, right? And our goal is to remove all of these words, right? I being the most common one, A and the other all value, basically words that carry little meaning. See any other questions? Okay. Is my wife waking right now?
No, sir, it's fine.
It's fine, right? Okay. Just let me know if it's so. This is one of the other things that we can do. Removing stop words, and what we'll do is that we'll from NLTK corpus list out all the stop words, and then the next thing you can obviously guess, we'll match if any of these stop words is present in our text or not. Right. So for example, for each token in our input, we will check if it is in the stop words library or not. If it is in the stop word library, we'll remove it. Right. So that's the general idea. We'll do a count vectorizer, fit transform, and then remove all the. This is a bit complex way of doing it, but the general idea what we are doing here is that we are doing a count vectorizer, right? Was word embeddings, sorry, word representation taught today? One out embeddings and everything. Yes. So just the idea is that we are trying to find a vector representation or a numerical representation of a word, right? Because our machine learning model will be operating on numbers, not basically words, right? So we need a way to represent a particular word in the form of numbers. So how we'll do it? We'll create a representation of our vocabulary. So let's say this is our vocabulary: bag, buy, cucumbers, eyed, going, high, mister. All of these are the different words, right? And black. So all of these are the words that are in our vocabulary. So for this to generate these words, this particular sentence, we need to know all of these individual words, right? And what we'll do, so we'll count how many times an individual word is in the particular sentence, right? So for example, and, as, both of these comes one time, black comes one time, buy comes one time, and words like some comes two times, right? So this representation of a particular string, right? So hi, Mr. Sid, this entire string in the form of a numerical vector of the length of vocabulary is called a count vector, right? So we have represented our entire input sentence, which is a string, in the form of a sequence of numbers, right? So the first word appeared one time, second word appeared third time, black appeared one time, buy appeared one time, and then at the end, sum appeared two times, right? So this is called a count vector representation. Another representation is one hot vector, in which 1 and 0 are the only values that would be present, right? So even if sum comes twice, it will be represented as 1, and let's say up was never in the actual text, we will report it as 0, right? So this would be the representation. We will try to represent our input text in the form of number. Okay. Is there any question?
Yes, sir.
Yes, go ahead.
Sir, is word embedding still in use because of the probabilistic model which are coming up?
Uh, just give me a second. Can you repeat?
Sir, I have two questions related to word embedding.
Hmm.
First is word embedding is still in use when we have more of probabilistic approaches?
Yes. Whether we are working with stronger or weaker model, we generally use word embeddings, unless it's just a very simple next word prediction model, right? Even in except for those cases, we will generally be using word embedding format. Some
Okay, and second, does word embedding take care of a sequence of a string, like what things is coming first and what things are coming later?
this particular kind of word embedding does not, right? But generally, when we move on to more stronger models, we try to introduce an information regarding the sequence or position of the word as well, right? Here we can see we have the sequence of vocabulary, right? So this particular my text is represented as 1 1 1. So all of these ones, 1 2 in the middle, and the rest are all ones, right? However, let's say some of the values were 0 somewhere, right? But if we change the sequence of the number of words in our vocabulary, this particular representation will again change, right? So what we try to do is that we ignore the positional information in certain kinds of factorizers or certain kind of word embeddings, but most of the recent word embeddings have a particular information, particular way where they store the positional information as well.
Okay, sir.
Right. So for example, the most common example would be, let's say, the word I have a very specific importance when it is stored as when it is used at the start of a token, right? Because that is, it would have a very high probability as a start of the sentence, right? So that is general idea. For example, the word am would have a very high probability if it is coming after the word I, right? So in that case, some positioning information needs to be maintained, and we cannot really ignore that. But since we are working with very basic machine learning methods, we will be starting with word embedding methods that are very basic as well. And these basic methods don't really store that sequential information right now. Later, I believe they would be introduced specifically in when we go through the intent classification or actual examples where we build systems that use these particular embeddings.
Okay, sir.
Okay. So the next way of doing things, someone is unmuted, I think. Just Ravi. Do you have a question? Okay. Okay. So the next part is of pre-processing is stemming. Right. So earlier we have gone through two particular steps, tokenization, and the second one was removing useless information. Right. So the third step is stemming, where stemming has another variation which is called a lemmatization. It's a variation. They are mostly different. Right. So the idea of stemming is stemming uses rough heuristics to reduce the words to its base words, while lemmatization does the same reduction, but it is based on vocabulary and morphological analysis. Right. So basically, stemming, you will just remove the end portions or start portions of a word, but for lemmatization, you would also focus on verb, noun, pronoun, and how the particular information is varied. Right. So for example, these are some popular stemmers available in NLTK: Porter stemmer, Lancaster stemmer, Snowball stemmer. The most common one used is generally Porter stemmer. And then WordNet lemmatizer is the most relevant lemmatizer, because since for lemmatizer, we are trying to get a general idea of the English language as well. So the number of lemmatizers are generally lower compared to the stemmers. So for example, we have all of these words: drive, drives, driver, drivers, and driven, right? When we apply stemming to them, all of these words would be reduced to the same base word, which is drive, D-R-I-V, right? So this is the base word obtained by cutting down extra portions from the words, right? So for example, from drive we cut E, from drives we cut ES, from driver we cut ER, right? So basically, instead of reducing the word to its base actual word, we get the base word by cutting words, right? Because all of you might know that the actual base word for this particular combination of, let's say, drive, drives, driver should be drive, right? So there should be a V, but we are ignoring the constructs of language in order to get our stemming faster, right? So instead of looking up how it is done in English language, we will just cut down text and then reduce it to a base, right? So that is the general idea of stemming. Now the next pre-processing step would be part of speech tagging, right? So idea of part of speech tagging is there are multiple part of speech for a particular text, right? Word, a particular token or a word can be noun, pronoun, word, adverb, anything, right? So what we want to do for our particular input, we will try to label each token as a specific kind of representation, right? And this representation will be called a part of speech, right? James is a what you call it? Noun, right? Smith is also a noun. Lives is a verb, right? In the determinant, and then United States are also nouns, right? Now these are predefined notations, right? NNP, VBZ, IN, DT, right? So it would not be possible for you to remember all of them. So instead of trying to remember all of them, it would be better you just use the particular predefined system to get the basic representations, right? Because trying to remember and basically mug up all of these numbers would not be very beneficial for you to learn, right? So the general idea is, so what I would want you to do is like understand the general idea of what we are trying to do here. We are trying to, for each of the token or a word, we are trying to correspond it to a particular part of speech, right? Similarly, these are the explanations of all the words that are coming up for this particular user input. James Smith lives in the United States. DT is a determiner. IN is a preposition. NNP is a proper noun. NNP is a proper noun that is plural, right? VBZ is a verb that is in the present tense, which is third person singular, right? So all of these distinctions are applied, and based on a particular number in the or basically character in the sequence, their definitions can change. For example, NNP and NNPS has the distinction where NNPS is for plural, while the first one is for singular, right? So these can be distinctions. I would recommend that you don't try to remember all of them, but try to learn how to get all of these values, right? So in order to get all the part of speech tags, you use the part of speech function that is available in nltk.tag, right? In order to get all the definitions of the tags, we use the nltk.help, right? And then append tag set gives us all the definitions, right? So it would be beneficial for you if you remember the actual functions instead of the values they produce. Right. Then the second important thing is named entity recognition. The idea of named entity recognition is that for a particular given user input, some values hold a very specific importance, right? And it could be made of multiple words, but they need to be processed together. Right. So for example, here is United States. So United States needs to be like processed as a single value. Right. Another example, let's say you're trying to book a flight from, let's say, New Delhi to New York, right? So in this sentence, the value New Delhi needs to be extracted and stored separately, and given the importance of source, and New York needs to be extracted and stored separately together in a, let's say, variable that would be labeled, let's say, a destination, right? So these particular kind of information needs to be extracted because they are very relevant to the task that we are performing, right? So we are trying to, let's say, book a flight, In that case, we require the source and the destination, right? So these kinds of named entity can be very relevant information to the task at hand, right? So these needs to be processed, extracted, and grouped together to make meaningful information, right? So this is the idea of named entity recognition. Generally, these kinds of tokens correspond to a physical object or physical entity. Let's right. That is why we are calling it a named entity. And the process of extracting is called named entity recognition. Right. So for example, we have the text James Smith lives in the United States. We are getting what tokenizing, right? Word tokenize my text tokenizes the my text sequence, and post tag is the function that gets us the part of speech tagging, right? Then what we do, we try to chunk it, right? How do we chunk it? This is our source. Person James, person Smith lives in the United States, right? So from here we can get that United States itself is corresponding to a singular entity, right? So this way what we are trying to do is we are trying to concatenate information that might be split into multiple words into a singular entity so that we can store it properly, right? Because if we do not do this, United and States, although they might be still extracted, but they will be stored separately and they would be useless, right? Because United and States by themselves don't really carry much information, but United States combined actually carries to a real word or corresponds to a real word entity, right? So this is the general idea of pre-processing steps, right? First was tokenization, converting a large text into smaller chunks of relevant information. Then we try to remove useless information. Useless information could be stop words, capital letters, all of these things, right? So sorry, stop words, uh, punctuation, and making all the text into lowercase, right? Then the third thing we did was stemming, where we removed all the useless part of a particular token to convert all the words into their base words, right? To make sure that we do not create specific like new entries for forms of a single word, right? Then we worked with part of speech tagging. The idea of part of speech tagging is to get uh, a particular representation for each of the token and then use this particular representation to get an idea of the structure of the word, right? The reason we were able to do this structuring of the word because we know that okay, noun follows verb, that follows preposition, that follows determinant, and so on, right? So this information about the structure of English language is available to us, and we use this part of speech to make sure that our this particular sentences corresponds to that structure of the English language. Right. All of this is not really used nowadays, right? However, since we will be working with basic machine learning methods from the start, it is important that you get a general idea of it, right? And I would recommend when we share all of these slides with you, you try to copy paste these particular codes and run it for themselves, run them yourselves. Okay. Again, this is the same idea of named entity recognition where we are trying to combine multiple words into a singular entity because individually these words carry a different meaning than the meaning that we are trying to convey, right? So we are not trying to convey black-eyed and peas as separate words. These particular words, when combined, hold a specific meaning, right? So instead of the meaning of the individual words, we are interested in the meaning of the phrase. And then compound an instruction. So what we can do is like we are creating a new tokenizer where what we are trying is that for the sentence you all are the greatest students of all time, we have defined that you and all should be treated as a singular entity, right? And of all time should be also treated as a singular entity. So when we apply our tokenizer based on this user defined tokenizer, NWE multi-word, right? It treats you all as a singular word and then off all time also as a singular token. Right. Through this lecture, I will using words and token interchangeably because they make sense as a starting point. However, later on, we'll be using the word, we'll be using tokens specifically because the more recent models generally do not work with word embeddings, right? They generally take tokens as a subwords. We will define what this means later as well. Right. So all of these methods you can use to reduce the amount of irrelevant information or to basically clean our data so that our basically compute starved systems can run and process these machine learning methods. Right. So this is a review of the process. First, we tokenize. Right. Tokenization can be based on sentences, word, anagrams, or some predefined constraint, which we can write down as a regular expression. Then we try to remove what we are trying to remove. We are trying to remove punctuations, capital letters, numbers, stop words. Now, this is a bit incorrect. We are not trying to remove capital letters. We just convert capital letters into small letters, right? So we do not, let's say, from United States, we will not remove U. We will convert U into lowercase. The third idea is chunking. Well, what we are trying to do, we are trying to group together specific tokens uh, to make them meaningful phrases, right? Or meaningful compound words, right? So for example, these could be named entities like United States or James Smith, or it could be compound terms, which can be dependent on user definitions, right? Of course, other than that, we can also apply stemming, right? We can also apply part of speech tagging. We try to remove misspellings and we try to make sure that our model works with different languages, right? We can also, instead of working with English, let's say we can work with Hindi, and for Hindi also we'll do the same thing, right? Some of the components of some of these methods shown might not apply to all the languages, but generally most of them should apply. Now we'll be going through one of the most common methods to use pre-process our data, right? This is okay. Let me just give you a different presentation. Okay. Yes. If you have any questions up to this part, right, you can. Stemming and lemmatization is useful in English corpus. Yes. What happens is that in nowadays the stemming and lemmatization very rarely used, right? Because we have systems that could use all the information that they have, and even removing like this er and es at the end of sentences is taken as a loss of information, right? So currently most of the systems are very data starved, and we do not want to reduce or lose any information, whether it could be like even if that impact of that loss of information would be minimal, right? So for any newer model, right? So any model that would be classified as deep learning instead of machine learning, you would not apply stemming or lemmatization. You would also not apply any stop word removal, because these stop words, even though they are not really meaningful, they give structure to the sentence, and that structure is also very important, right? So for the newer models, all the information is kept, right? So the text that is there is parts generally as it is, or we employ someone that can convert badly written sentences into proper English sentences, let's say, or in any other language, whether Hindi or English, right? So that's the general idea. Whether it is stemming or lemmatization, most of these concepts that I'm telling you are not generally used recently. Okay, Vivek Tripathi.
Sir, you talked
Yeah.
about POS tagging.
Yeah.
Will this POS tagger will work for a Hindi statement and will correctly identify the
Okay.
syntactic
This
way of
particular example that I gave you, right, uses a specific tokenizer, which is only there for English language. Right. So for example,
so
the
do we have
tokenizer,
any POS tagging for
yeah.
Hindi language?
I'm not sure if NLTK library itself has it. I believe Spacey has some Hindi tokenizers, right?
Sir,
You can.
I am specifically willing to understand if there is any standard which is there in the computational linguistic world of identifying
Mm,
syntactic categories for Hindi lexical items.
there is not really a standard I can say because it is hard to be like complete for natural language, right? So there are just like standard in the terms of there are 5 or 10 ones that are primarily used, and you use the ones that you can basically afford to run. Right. So for example, you use Spacey one because it's the smallest one that it's the largest one you can run. Right. So that's an idea. You try to use a model that is the largest you can run on your system at the time. Spacey models for Hindi language that apply this part of speech tagging can be a good point to start. I am not 100% sure, but I believe Triple IT Bombay and Triple IT Madras have some better ones. Right. You can go ahead and look into their labs, and then I believe they have some better ones than the ones that are already available in Spacey because those are a bit old, while the ones that are there are generally better. Or you can just check out Bhashni, which is like a government of India initiative, which basically is a like collection of all the work that is done in Hindi languages. Right. So I believe there is a position there for part of speech tagging. I'm not 100% sure because specifically this I don't think I have worked with because part of speech tagging is a bit rare now.
Okay, so they are not using for English language as well now.
No. English language they definitely don't use, right? Because the idea is that only if no, even if it has some complex problem like pragmatics or anything, it is generally not used. Most of the language models, what they do is that you have a huge amount of data and then you just try to learn the patterns in the data. And the most common way of doing that pattern analysis is trying to predict the next word. Right. So you have 10 million words, let's say, and based on the first word, you predict the second. Based on the first two, you predict the third. Based on the first three, you predict the fourth, and then you do this on. And you do this for billions and trillions of amount of data, and then your model just learns how to uh, respond. Right. So what they are trying to do is not try to do all of these part of speech tagging, chunking, stemming, etc., but just train a model on a absolute huge amount of data and run a model that has a very high number of parameters. Yes. So most of these techniques are basically good for a starting point because they introduce basic concept that will allow you to learn the importance of what the technology that is used right now, why is it that useful, right? Because we had some issues with the older technology like faster speech tagging and so on. That is why we went ahead with the methods that we use nowadays. Right. I hope that part is clearer.
Yes, sir. Thank you so
Okay.
much.
If you have any other questions, you can go ahead as well. Uh, hmm. Any other questions? No, right? So let me just stop sharing my screen. I have actually uploaded the wrong code. Let me just check the correct code and give you a demonstration. Uh, No. Okay. Hello everyone. I'm audible, right?
Yes, sir.
Yeah. So one attendance sheet was shared with you guys, right?
Yes, morning it was shared.
Yeah. So the one that Gunjan shared, I'm sharing that link again. Please mark the attendance for the second part as well, right? Those who have not marked, because there are two entries for the third day, right? So mark that as well. Yes. So I'm just I've shared that link again. Mark the entry for 3rd of March as well. There will be two columns for 3rd of March, right? Yeah. Okay, everyone. So have you marked your attendance?
Yes, sir.
Okay. Okay. So here, let me give you an example. Shit. Sorry about that. I had the file stored somewhere incorrectly. Right. So let's say this is an example of simple tools that we'll be using with machine learning. Right. Most of the common tool that is used with machine learning to handle data is called the pandas package. Right. A pandas package holds a good bunch of tools that allow us to basically look and study the data. Right. For example, these are all the packages that we'll be using. SpaCy is a package, as mentioned earlier, was a package with a bunch of language resources. Right. NumPy is a specific package that allows us to use numbers in Python. Right. So, for example, arrays, all of this information. So, for example, I'm not sure if you know, but in Python, arrays are not there, right? So list is treated as an array, but list can have values that are of different data types as well, right? So in order to basically process data efficiently, we need arrays of basically numbers, right? So NumPy allows us to use those arrays of number and basically speeds up all the processing that we have substantially, right? So that is the general idea of using why we use NumPy. And then one nifty thing about Python is that you can import the package with a secondary name, right? So for example, each time you use a function or a class that is available in the package NumPy, you would have to write NumPy dot again and again, right? So you can, instead of using the entire name multiple times, you can use a small abbreviation or a short form of particular package name as well, right? So we are importing NumPy, but instead of writing NumPy every time, we will be writing NP, right? Again, we also use the package matplotlib. Matplotlib is a package that is used to basically plot information or plot any relevant information that we have for a particular data set in the form of, let's say, histograms or any graph. We can use matplotlib. Seaborn is another basically it's another package that is built on matplotlib as base, right? And allows for a different or more number of plots and graphical representations, right? Now, the benefit of matplotlib is just because it is a lower level function, right? A lot of customization on it is possible, right? However, since Seaborn is mostly a high level function, the amount of customization and changes on it is a bit limited, right? So what we'll try to do is we'll try to first load the data set, right? Let's say we are working with this kind of data set. So I've downloaded the data set somewhere. Uh, so the first data that we are trying to read is the multi-dogo data set, right? And from that data set, we are trying to read the training file. So in machine learning algorithm, we have three kind of files that we mostly use, right? For example, here in multi-dogo system, you can see that we have three kinds of files. Train, dev, and test. Right. So train is used to train the model. Dev is used to evaluate or test the model while the training is going on. And once the entire model has been trained, we use the test set to get the real world performance of the model. Right. .tsv extension is for tab separated values. You might have heard of with Excel sheets, right? So it is kind of similar idea where the data is data is in the form of a table. Right. Right. So this is the kind of idea of, let's say, the data. Our data has these many rows, sorry, these many columns. The first column is conversation ID, which corresponds to this number, right, or this string. The second value is turn number, which starts from 0, then goes to 2, 4, 6, 8. Right. So turn in a conversation describes the order. Right. So 0 represents the first sentence spoken in a conversation, 1 represents the second sentence, or 2 represents the third sentence. And the idea is it's a conversation happening between two parties. So 0, 2, 4, 6 generally corresponds to one speaker, and 1, 3, 5, 7 would correspond to a second speaker. Right, that's the general idea. However, you can see here that 6, 7, and 8 corresponds to a single speaker here. How? Because one sentence, the information they provided by providing 3 sentences consecutively. Right, this can happen as well. So this third column or the third feature for our data is sentence number. Let's say sentence number is 0 for all of them. Utterance ID corresponds to the utterance ID, which is generated by using the CONV special token followed by the corresponding conversation ID. Right. So basically this conversation ID is directly copy pasted here. Then the special keyword turn followed by the turn ID for this particular entry, followed by the special representation for sent, right, which corresponds to the sentence number and the corresponding sentence value. So this fourth column is generated entirely using the columns 1, 2, and 3. Right, that is the general idea. Similarly, we have rest of the important information where we have the utterance, the actual sentence that was said, the slot labels, right, because there was one word spoken, right, so we have 0 as the slot value, right, and opening greeting is our intent, or the intent is the idea that based using this particular sentence, what is the task that user wants to fulfill, right? So by saying hello, the user wants to perform a greeting. So that is the general idea. So for example, I would like to purchase the internet connection, right? By using this particular sentence, the user wants to start an internet service, right? That is the intent. So that is the general idea. The intent refers to by saying the particular sentence or by saying the particular utterance, what is the task the user wants to be fulfilled, right? And this particular, what was the second last thing? Slot labels corresponds to all the relevant information, right? So what is the relevant information? First value is 0, which means I is useless to us. Second value is also 0. Would is also useless to us. Like is also useless. To, purchase, and the is also useless. Internet is important information and corresponds to the information type of service type. Right. And again, connection is also useless. Right. So basically, whenever you try to work with a particular machine learning model for the type of data, it is very important that you go ahead and try to understand what the particular data represents. Here, our data represents the first column is conversation ID, second is turn number, which is the number of the utterance in the entire conversation. Sentence number is a number given to the sentence. We have defaulted it to 0. Utterance ID is generated by combining conversation ID, turn number, and the sentence number. Then we have the actual utterance that is spoken, all the relevant information or entities, named entities that are present in the text. And then finally, what is the task that the user wants to perform by given that particular sentence or input. Right. So that is the general idea. This is the data that we are working with. Right. So by using df.head, right, what we can do is print out the first 5 sentences or first 5 entries from the table. Right. By providing df.head 10, you can also print out the first 10 values as well. Right. Generally, the idea is that you do not want to see the entire data. You only want to see the starting, let's say 5, 10 values, or maybe you can also enter 10 colon 15. So from the 10th position up to 14th position, right? Because generally Python goes from 0 to the current position to n-1 position, right? So it will go from the 10th row to the 14th row. So 5 values, right? So you can write like this to generate the corresponding sentences you want to, sorry, corresponding rows that you want to see, right? So all of this is TN test, and then you want to see relevant information from the data, right? How do we do it? We try to clean our data. df.cleaner is equal to df.train.goodbye intent dot size dot reset index, right? This is a bit complicated function, but what we'll do is try to tangle try to tackle all of these particular operations one at a time. So df.train, we have already seen df.train. It is this first data set, right? Group by intent. So intent is the name of the column that we want to first work with, right? Intent is this column which corresponds to the task that the user wants to perform. So what we are trying to do, we are trying to group by the task user wants to perform, right? So for each task, let's say there are 500 sentences where the user tries to open with a greeting. There are 600 utterances or 600 sentences where the user tries to start a service, right? So we'll try to group all of these sentences based on the goal task at hand. Right. Let me just check if there are any questions. Okay, fine. Right. So the second thing we did is group by, where we are trying to group the utterances or basically all the rest of the information, basically constant conversation ID till slot labels based on the intent, right? Based on the task that we are trying to perform. Then the third thing is size, right? And then reset index name to count, right? So we are focused on the counts for each of the intent, right? So here we get that for the unique task or intent of cancel service intent, we have count of 6, right? So we have 6 utterances that have the intent of cancel service intent. Then for closing greeting, we have 439. There should be somewhere opening greeting. Opening greeting is 1581. So people start with a greeting, but not necessarily end with one, right? Content only is 3700 utterances on all of these. So by using this method, df.train.goodbye, we are able to get examples for how many types of particular tasks that the user is trying to perform. Here we can see that from 0 to 17, the user is trying to perform 18 different kind of tasks for our given data. Right. So all of this information we need to get before we start working with our data. Right. So how many unique tasks that the user is trying to perform, how many kinds of unique information the user tries to perform, all of these kinds of things. Right. Now, again, the idea is data cleaning. As I said earlier, data cleaning is not necessarily performed, right, for the actual sentences, but in a tabular data, there are some columns that are useless to us, right? Irrespective of like whichever task we are trying to perform, some columns just are not of interest to us, right? Or maybe some intents are not of interest to us, right? So all of these things needs to be dropped again, right? Maybe some particular intents have very low number. Like for example, cancel service intent has only 6 example. If we try to train a model, the model will not be able to perform well for this particular kind of task because there is not enough data to learn that particular task, right? So that is the general idea. If there is tasks that have or intents that have low data, right, either you want to remove those particular tasks so they do not corrupt the model, right, with useless information, or we want to collect or generate new examples for these weak samples, right? So that is the general idea. Here we are not interested in really the exceptional performance of the model. So we'll just go ahead and remove the particular intents that are of no use to us. So this corresponds to the cleaning that generally happens in actual coding, right? We delete the information that is not of no use to us, right? That not of any use to us. In traditional machine learning, it corresponded to stop words and things like that. But in tabular data, the data that we are working with, it would correspond to intents or tasks that have very few examples, right? So that is the idea. Again, all of these examples we pick up intents that have less than 100 of count, right? So this update account info, transfer service intent, all of these update service intent, all of these have less than 100 examples, so they would be removed, right? And then we use the function df.train.drop I in place equal to true, right? So what is this function? I is a row in intents to remove, right? So any row that has an intent which we want to remove. So any row from this data, let's say start service intent we want to keep, open greeting also we want to keep. Let's say here, so there, let's say there was an entry for the intent upgrade amount info, right? Sorry, transfer service intent. So what we'll do, this line, it will check if the particular entry in our data set, which is df.train, df_train, if any of these values corresponds to the intent or corresponds to the task of transfer service intent. All 8 of these entries would be removed. That is the idea of drop, right? So drop will remove all the columns that have intents that we have defined as intents to remove. And then we do this thing again for the test set, right? For the training set and the test set, we remove all the intents that we are not interested in. And these intents would be the intents that have less than 100 samples, right? And this in place is a special like method. Now, generally, if you have used any programming languages, if you want to overwrite the value of df.dftrain, right, you will write it as something like this, right? Df is equal to dftrain, the original value of dftrain, and then drop all the elements that are an intent to remove, and then replace the old dftrain with this new value, right? So this is how we will generally overwrite an old variable with a new variable, right? Using this assignment operator. However, pandas allows us to, instead of doing this assignment, just update our data set or update our data frame by using the keyword in place, right? In place equals to means that all of the changes, which is in case drop, persists, right? That is the general idea. Now, after removing all these examples, again, we can check that how many intents or tasks remain. And we can see here that only 10 tasks remain. 8 tasks are gone. So this is the idea of cleaning here. Now, these are also relevant information for you, right? We will only cover till here, right? Because most of these topics are included in classification, which I believe will be taught tomorrow, right? I don't think classification has been taught yet, right?
No, sir.
Okay. So what we'll do for today, we'll only be focusing on how to clean. So because for training is a two-step process, right? First we'll clean the data, then we will implement the data. So today we'll only going over the cleaning part, and for the actual implementation part, we will probably go and do it on tomorrow's session or day after tomorrow's session. You guys have the tutorial, right? So day after tomorrow, we have a tutorial classification. There we'll go over the same example again. We'll be going over how to actually use these after we have cleaned the data, how to actually use them in an actual model, right? But the general idea is that we are focusing currently on what are the basic practices for natural language processing or any textual processing, and then these concepts are done in multiple ways for a particular method, but the concise idea, right, that we want to clean our data by removing useless information, that is consistent across whether we use tabular data or whether we use textual data. Right, even if we were to use image data, we would do something similar, but we'll not be going into that because that is not really my area of expertise. But for the most part, whether it is textual data or tabular data, we want to clean our data or you remove any useless information from our data. Right. Similarly, we can see here, we had all of these counts available here, and we can use functions like packages like Seaborn on Matplotlib to represent our data in different forms. Right. So for example, here it is for the class which is labeled 0, we can see closing greeting. We have around 500 examples, right? A little under, let's say around 450 examples, something like that. For class 1, we have around 2000 examples, confirmation, right? And similarly, we can plot and see that, okay, class number 2 has a lot of examples. And because the class number 2 has a lot of examples, there's a high chance that when we train the model, the performance for class 3, class 9 would be suffering, right? Because the model does not, our data does not represent these classes equally, right? And because the data for some classes is more, because of, so correspondingly the model would be more biased towards certain classes, right? So we have to visualize these kinds of things. Generally, there are methods to remove these kinds of issues as well. One of the most prominent method is to generate synthetic data, right? So create more examples of the same kind of data. So for example, this is one sample for data corresponding to service intent. You will generate another sample with very minor modifications to the word I need internet. So something like you need internet, and then by this way generate synthetic data, right? Uh, by this using this synthetic data, we can increase the number of samples for a particular weak class and then try to make our data more balanced and subsequently our model more robust. But generally, since that particular is the focus for this particular tutorial, we'll be stopping with this only. Right. If you have any questions, you can go ahead and ask. Right. The slides, share the data encode. Yes, I'll share the data encodes maybe in half an hour or something. Once we have checked all the files. So the data, so basically we'll be sharing all the content from the first, second, and third sessions by the evening. Yes. Okay. So if there are no more questions, we can end it. Right. I would recommend that once you have the code files available to you, you try to upload these files and the data onto Colab, or if possible, you try to install basic Python on your system and try to run these files, right, once and see if you are able to run these files or not. If you're not able to run it, you can send a message on preferably Google group, because the actual lecture sessions are quite stacked, right? So you might not have a time to interact and ask questions during the actual sessions. So if you are facing any issue, you can write emails as well. And just make sure not to make multiple emails on the same topic, right? And in that regard, try to keep precautions there on. Okay, any other issues?
Sir, before we end this session for today, I just wish to remind that Professor Eric, he told us that he will share his book of NLP. So can you
Yes,
also
yes.
incorporate that?
Yeah, he has shared it with me, and I'll just share it with you guys as well. Right. So I don't think he has shared the entire book. He has only shared first like 5 pages, but IIT Patna has access to download the book. So I'll download the book and share the entire thing with you guys. Okay.
Okay, sure. We got his slides, but the book is not
Yeah,
there. So
slide. I think there should be a link to his book in the slides itself, right?
Yes, sir. Sir, slide is there. So I got you the slides, but not the book.
Okay, okay. So I'll just look it up. I believe we have access, and we will just send you the entire books on the Google group anyway.
Thank you, sir.
Okay. Also, if you are not able to run the codes or if there are problems with files, also let us know. Okay. Just in case. Okay. I hope all of you have marked your attendance. Right. In case you have not, please do. Otherwise, we can end the session now. I'll just,